Welcome back, everybody, to Simple Harmonic Motion. Today we're going to be diving more into the period frequency and angular frequency of this topic. All right, so I'm going to first start off with a little video here. This video is just to demonstrate that simple harmonic motion and uniform circular motion, even though physically they are doing different things, if you look at it from a math perspective, what's happening is very similar, which I'll be talking about in this video. So if we were to look at this video, what we should notice is in the bottom, we're going to have uniform circular motion with this block going back and forth as you see. And at the top here, we're going to have uniform circular motion with this circle thing going in a circle like uniform circular motion is. However, what we're going to notice is their motion in the x direction is going to be the same. So how they move in the x direction, how long they both take to cycle, is going to be the same, whether they're going in a circle or directly left and right. So let's kind of play the simulation and then we'll see how this all works. Okay, so you can see in the x direction, they're taking the exact same path. Okay? So if they're taking the exact same path and the cycle is taking the exact same amount of time, what this is telling us is the period is exactly the same. So the period for simple harmonic motion and the period for uniform circular motion will be equal to each other. So mathematically speaking, they're going to have the same. We can use this mathematically. We can use the same period to find out what the period is for each of them. Okay, and then we get this equation here. So this says that all the energy at the maximum velocity is equal to all the energy with the elastic potential energy. So all kinetic energy max is equal to elastic potential energy max. And we can use this formula. Velocity is equal to 2 pi r over t because, again, remember, the motion, even though it might be different, mathematically it's the same thing. So we can use this velocity and we can substitute it with 2 pi r divided by t. We could also substitute this a, which is the amplitude, with whatever the radius of the circle is. So what the radius. Okay? And it simplifies to this formula here, t equals 2 pi square root of m over k. This is where we get that formula. The period is equal to 2 pi times square root of mass over k. Okay? And this is off the basis that simple harmonic motion and uniform circular motion are the same thing mathematically speaking. Okay, let's look at some examples. A spring is mounted horizontally with its left end fixed. A force of 6 Newton causes a displacement of 0.03 meters. A 0.5 kilogram glider is placed on the frictionless air track and pulled 0.02 meters and released from rest. Find the force constant of the spring. Okay. So one thing that we should know is when we're applying this 6 Newton of force, it moves 0.03 meters. What this is telling us is the force of the spring that we put is equal to kx. So we're applying a force of 6 newtons onto the spring. We don't know what the spring constant in k is. That's what we're looking for. But we do know it stretches 0.03 meters. What this tells us, if we were to use our calculator, 6 divided by 0.03, that the spring constant is equal to 200 Newton per meter. Okay. Now we want to find the angular frequency and the period and frequency. Well, actually, what I'm going to try to do first is I'm going to find the period. So period is equal to 2 pi square root of m over k. So I'm just going to plug some things in. I know m is equal to 0.5, and k is equal to 200. We just found what that was. So now I'm going to put this into my calculator. 0.5 divided by 200 times 2 pi. And we should get around 0.31 seconds for every cycle. That's how long it takes to make a full cycle. Next, I'm going to find the frequency. Again, we should know frequency is 1 over period. So that means that we could do frequency is equal to 1 divided by 0.31. That means, okay, 0.31. So 1 divided by 0.31. And we should get around 3.23 hertz. Lastly, what we're going to be looking from part B is this angular frequency. Again, we should remember angular frequency is equal to 2 pi divided by t. Same thing as the simple harmonic motion. So I'm going to change this t to be 0.31. And then what we get, 2 pi divided by 0.31, should get around 20.27 radians per second. Okay. Hope that all made sense. Okay, moving on. An unknown mass is attached to an ideal spring with a force constant of 120 Newton per meter. It is found to vibrate with a frequency of 6 Hertz. Find the period of motion. Okay, so again, we should know the period is the inverse of the frequency. So if this is 6, then we know that the period is equal to 1 divided by 6, which is 0.167 seconds. And maybe I'll take some time to talk about what this means. This means that it makes a full cycle from here to here in 0.167 seconds. So every 0.167 seconds, it makes a full cycle. What frequency being 6 Hertz means is in 1 second, it goes back and forth 6 times. So that's what frequency means. It goes back and forth 6 times in 1 second. Having a period of 0.167 seconds that's how long it takes to make a full cycle. So angular frequency. Again, 2 pi divided by period. We found period as 0.167. And this is going to give us an angular frequency of 2 times pi divided by 0.167. Around 37.62 radians per second. 37.62 radians per second. And now what is the mass of the body? So what we should know, period is equal to 2 pi square root of m over k. Now I know period is equal to 0.167 and it's equal to 2 pi. I'm putting this in parentheses because I'm going to end up dividing 2 pi, and pi is strange. You want to make sure to always put this in parentheses when you divide. So square root of m divided by k, which is 120. So let me do this. 0.167 divided by parentheses 2 pi. If you do 2 pi, depending on your calculator, you might get different results. Squared times 120. But if you did everything correctly, you should get a mass of around 0.085 kilograms. Okay. And moving on. A 0.2 kilogram air track glider is attached to an ideal spring of negligible mass and starts oscillating. The elapsed time from when the glider first moves through the equilibrium point to the second time it moves through the equilibrium point is 2.6 seconds. Find the spring force constant. Okay, so we're looking for what this K is equal to. But what we know is from here, and then to oscillate and come back to this point, this takes a time of 2.6 seconds. What we should know is the period would be if it started from here to go back here, to go all the way here, but then to come back to the same point and same velocity. So this is a full cycle. So the period is actually 2.6 times 2. So the period is 5.2 seconds. That's a little bit of the tricky part of this question. Now that we know that, we should know that the period is equal to 2 pi times square root of mass over k. And now we could just plug some things in. 5.2 is equal to 2 pi square root of mass, which is 0.2, divided by k, which is what we're looking for. So let's do this. 5.2 divided by parentheses 2 pi squared. Now I'm going to do 0.2 divided by answer. And I should get around 0.29 Newton per meter. Okay, so a pretty low spring constant. Okay, let's look at this example. Example number 9. An object is undergoing simple harmonic motion with a period of 0.9 seconds and an amplitude of 0.32. At t equals 0, the object is at position 0.32 and is instantaneously at rest. Calculate the time it takes the object to go from 0.32 to position 0. Okay, so let's look at this. First off, we know that this is the equilibrium and it's all the way at the amplitude, which has an amplitude of 0.32 meters. We want to know how long it takes this object to go from here to here. Okay, that's how this is position 0, and we want to know how long it takes to go to that time. What we do know is that the period is equal to 0.9 seconds. So let's think a little bit about what the period is. So the period means it's going from here all the way to the other amplitude, the negative amplitude, all the way back to the equilibrium, and then back to where it started. That would be the period. So what this time is going to be equal to, we're pretty much going to be doing this 4 times. So if 0.9 is the period, from here to here, that is going to be 0.9 divided by 4. And 0.9 divided by 4 is going to give us 0.225 seconds. All right, I hope that made sense. Next time we'll be talking about graphs, which is a huge part of this chapter, and a little bit more tricky than what we've been doing so far. Thanks for watching, guys. I'll see you with the next one.